much. Thank you for the opportunity to speak today and the opportunity to represent our team at the University of Colorado. We have quite a strong team, and I feel that they are all equal partners in this venture. So very fortunately, we were able to receive a grant from the Bill and Melinda Gates Foundation in round 2 of Reinventing the Toilet. It started 6 weeks ago, I believe, so you're going to see our concepts in the direction that we're heading, and I really would appreciate feedback. It's been quite nice to be at this conference. I'm coming from the drinking water sector and not the sanitation sector, so I'm here to learn, and it's been a great experience to date. Basically, we want to condense the sanitation value chain into one location. So we're looking to design a toilet that's affordable and desirable for use, renders the fecal waste harmless within a short time span. It's self-contained without the need for flushing water or electricity, and it produces a valuable end product. Our approach is rather straightforward. We want to use solar concentrators to capture solar energy, and then fiber optics to transmit that energy to a high-temperature thermal reactor, and then to inactivate the waste material in this high-temperature thermal reactor and produce and create a useful end product. In addition to the prototype that we want to develop in this 15-month period, we also want to advance the science in terms of our knowledge dealing with fecally derived biochars. We have experience with biochars from other feedstocks, but this is the first time that we've used fecal material as a feedstock for the production of biochar. We also want to advance the nutrient and energy recovery systems from urine and gases that will be released during the pyrolysis process. And also advance the use of fiber optics for transmitting energy from solar collectors to high-temperature reactors. Our project plan over this 15th month is outlined briefly here. We're in the stage of proof of concept on paper, and we've also started some reactors in the laboratory. We hope by April of next year to have validation in the laboratory, and then August to have an integrated prototype of next year. So about a year from now, we want to have the prototype in place in a semi-controlled setting, and then move into the technical readiness level 7 thereafter. Our project team is organized here. Is there a pointer? No? No pointer? No, that's fine. We have Carl Hensman. Carl's here today as our program officer, and then Carl Linden, faculty member in environmental engineering, is the PI. And then Al Weimer, chemical engineering professor, and myself serve as co-PIs. Corey Oversby is the project manager. And we're very fortunate to have a project consultant who's an adjunct professor, Dr. Rita Cleese. Rita has 25 years of experience in the water and sanitation sector with the World Bank. And she's the one that we go to try to keep things real. She's the one who sits back and says, okay, you technical geeks, you know, that's not going to work. And let's make sure reality is part of what we do. So Rita has made a major contribution to what we do. And the design teams are divided into 3 groups. The solar team, the reactor team, and that kind of left-hand side of this diagram is made up of the chemical engineers on the project. So the chemical engineers are working on those 2 phases. And then the right-hand side of the diagram, shown in green, of course, are the environmental engineers, and those of us with a background in absorption in the biochar. And then we have one environmental engineer, Tesfa Jacob, who is the lead on the integration team to bring these 3 teams together. in a way that will produce a useful product. This is our concept. It's rather simple. We'll collect the fecal material, and we'll talk about the different forms that we collected. And we're going to use a reactor that's, depending on the size, we'll collect it in maybe a 4 to 6 liter container. And over the course of 20 hours during the day, that material will be collected. And then we will have it on a carousel. And then the carousel will be turned around so that it is now placed underneath our reactor. So the turning of the carousel and the dropping of the reactor onto the collection container can be done both electronically with a manual backup. So without any electrical energy, the system should work totally mechanically. We then, over the course of 4 hours in the day, collect the sunlight and the energy from the sunlight and transmit that energy through fiber optic cables to the reactor. And when the reactor is lowered over the storage container, then we'll have a reaction taking place at high temperatures from anywhere 300 to 800 degrees C. After the 5-hour period, we'll have a product that will then gather, and we hope that this product will meet the qualification of a biochar, that will have some added benefit in an agricultural additive. We're going to consider 3 different reactions, processes that are taking place. The first will be mixed waste, where we have both feces and urine together. And the second will be a urine diverted solid waste. We'll carry both of these reactions and reactors all the way through to our final prototype in the development. We'll also look at hydrothermal carbonization, and we'll look at that at least at the bench scale. The problem with this is that we need to pressurize the reactors. For both pyrolysis reactors, they can be at 1 atmosphere, so there's no pressurization that will be needed in those cases. We just need to exclude oxygen from the reaction so that we keep it in a pyrolysis domain. And we just do that by bringing the reactor down on top of the cylinder with no major types of sealing involved with that. So the HTC will be carried out at the bench scale, and then if it looks promising, then maybe in a phase 2, we'll bring the HTC along at the prototype level. This is our estimation of the energy requirements per person for these 3 different systems. And what we can see is that the energy for both the hydrothermal and the mixed waste pyrolysis is around 3,500 kilojoules per person. And based on the assumption of a given amount of waste collected. And the energy for a urine diverted system is quite lower, about 1/3 of that. And the reason is that most of the energy is taken to drive off the water from the system in the other 2 processes. So we have to heat that water up to 300 degrees, and that's where most of the energy loss is. To go in any of these systems, once the water has been driven off from 300 up to above 700, requires very little energy addition. So this gives us a relatively wide range of reaction temperatures that we can work in without having much additional energy put into the system. So our experiments at this time at the bench scale are looking for where in this energy range or the temperature range of 300 to 750 do we produce the best biochar product for use. The solar concentrator concept is to take a parabolic concentrator, gather the energy from the sun, and then use fiber optics to transfer that energy to our reactor. And so the nice thing about the fiber optics is that the cables are flexible. We can locate the reactor where we want in proximity to the reactor, and then bring the cable in and attach it to the reactor. And they can withstand these high temperatures and transfer energy under these high temperature regimes. These systems have already been produced, generating temperatures above 800 degrees C. This shows a system that's in use for processing lunar soils. The concentrator design parameters, we're working with the assumption that we'll only have 4 hours of sunlight in the course of the day. And in that time, we'll be having 800 watts per square meter of sunlight will be the density of the sun, intensity of the sun. And we're going with collectors that have 0.6 of a meter in diameter. So they're about this size in diameter. A small satellite dish that's used for television communication is what the vision that we have on. So if we use those discs and we assume an overall efficiency of 50%, which is quite high, and that's what the fiber optics bring to the system. There's a very high efficiency of capturing the sun from these coated parabolas and bringing that energy into the reactor. Only a 50% loss to the system. That means that we're delivering to each dish about 100 watts of power to the system. We envision an array of 8 of these concentrators, and each concentrator will have a bundle of fiber optics attached to it. So that means that we'll have 8 fiber optic bundles moving down and attaching to the reactor from that location, from each location of the collector. With 8 of these collectors, we can serve a household of 4 to 12 individuals. And so what we're looking at is based on either dry pyrolysis or wet pyrolysis. If we have a wet pyrolysis situation where there's no urine diversion, then these 8 collectors will provide service for a household of 4. We move to dry pyrolysis, so that's about 2 reactors per person, 2 collectors per person of this size. If we move to dry pyrolysis, now we're only looking at 8 collectors providing for 12 people. So that's 3 collectors of this size providing enough energy for 4 people. So 3 collectors of this size providing enough energy for 4 people. Each of the collectors we estimate with the fiber optics to cost $80 for the system. Each collector at $80. Each concentrator, not the whole collector. This is what our reaction chamber looks like. We have the waste coming in to our reactor on the right-hand side. The reactor will need to be stainless steel to withstand these temperatures of 300 to 750 degrees. So there'll be some investment in a high-cost material at that point. They'll operate, we envision, about a 20-centimeter diameter for the reactor, and then the depth may vary based on the volume for the particular household. What else was I going to say about that? Approximately 1 atmosphere is the pressure that will be in the reactor if we're not using the HTC process. We then have a carousel, and we'll spin the collection system around so that it's now positioned underneath the reactor itself, or the reactor cover itself. And this, we envision having a servo motor to do that, but also with a mechanical backup for the system, so that it can be done completely mechanical. And then both electronically with a mechanical override, we will lower the reactor on top of the container, and we can see where the fiber optic cables come in and light enters into it. We've showed 3 of those on here, and there'll be, for our standard collector, there'll be 8 connections made. And then once the reaction starts, the gases will exit through the top of the reactor. The outer wall of our collection system will be material that has a high infrared and visible light absorbing surface so that the energy will be transferred into the reactor. And then the cover, or the inside part of our collector concentrator connection system will be coated with a very reflective surface so that as the energy comes in, it will reflect off the outside of this part of the reactor. And then the outer chamber will be designed to make sure that we protect the fiber optics. Of the whole system that we're talking about, the fiber optics are the highest cost of the system compared to everything else, the collectors and everything else. The majority of the cost ends up being in the fiber optics. And our total cost for the dry pyrolysis system, we're estimating to be $800 that would serve then a family of 12. So this is where the chemical engineers get involved. They have these nice heat transfer tools. The reactor will run for 4 hours, heating the waste up from 30 degrees C to 750 degrees C. To date, our modeling hasn't taken into consideration the phase change from water to steam. It hasn't taken into consideration the radiation exchange between the outside walls of the reactor to the inside storage container. We also have to figure out the inefficiency of having the cables connected at different locations and the transfer of the heat at that point, and then the shape of the material, the fecal matter inside. At this particular point in time, it's assumed to be homogeneous, and we know that that won't be the case. But we'll apply those into the model and move forward to fine-tune the energy requirements and the efficiency of our system. Our desired product is a biochar. And what do we mean by a biochar? There's many definitions around anything that's a final combustion project from biomass. Is some definitions, but for our purposes, we want to have a carbon-enriched solid product of thermal biomass decomposition. And it's largely made up of condensed aromatic or graphitic zones that when applied to a soil imparts an agricultural benefit and is recalcitrant over a long period of time. So those are the measures that we want to characterize our material. At this point in time, we don't think that fecal matter will result in a definition of the biochar that's oftentimes used. But we want to look at how we can change the reaction conditions to produce a true biochar. To characterize the biochar, then if we look over on the right-hand side of this definition with the functions, we'll see the things that we think are important to make a good biochar. We're going to characterize the surface area because the surface area, and we're looking for something like 10 to 20 square meters per gram, is important in the accumulation of organic material, accumulation of microbes, for the establishment of a community structure, and the retention of any inputs in the system, including moisture. The cation exchange capacity will be very important because this will lead to retention and the bioavailability of the nutrients. And we also want to look at the buffering capacity of the material. In terms of the soil additive, it's very important that the biochar adds stability. And then the longevity. If the biochar is going to be considered for CO2 sequestration, then the biochar has to be around for a while for the system. One of the attributes that many people make with the biochar is that it's sequestering CO2 in the system. But if it doesn't stick around, then the CO2 sequestration is not really much of a benefit. We realize that we may not meet the definition of the biochar, so we're also going to test our solids residuals from this reaction using other definitions of fertilizer, compost, and biosolids, and we'll be running additional tests that will help us classify our final material within this realm. Our lab testing by two of the workers on the project will verify the waste stabilization, and as I said before, it will give us the information that will allow to classify this according to the accepted standards that have been developed. And then, in addition to that, we want to really focus on optimizing the process. What temperature, time, conditions do we need for both wet pyrolysis and dry pyrolysis, as well as HTC, to be able to generate a product in an efficient way. Nutrients are a valuable asset within our nutrient-rich waste. But if we go to urine diversion, then we'll be taking nutrients out in the liquid. And if we heat the material up to form our byproduct solid, then we'll be releasing gases. And there's valuable content, both in heat and nutrients, in these pathways that are escaping away from our solid. So we want to take this biochar, the solid, and reuse it to help capture the value in the liquid and in the gas streams. So we'll reapply this final product to help capture the nutrients from the diverted urine. So we'll pass the urine through the biochar and collect the nutrients. And we'll also pass the gases through the biochar that's been produced and try to capture other types of materials from it. In addition, we need to be able to work with both human feces as well as synthetic feces. Our biggest problem is figuring out how in the laboratory to have a very consistent product that we can test so we can make comparisons from one test to another test. And with human waste, that becomes very difficult. So we're looking for a synthetic fecal material to look at, but only from the perspective of the final product. So we're going to look at different recipes, synthetic recipes, that will produce a similar type of biochar, not driven by other characteristics of this synthetic material, but only driven by what it produces within the biochar. We're also going to, as I said before, look at the off-gas characterization and recapturing the heat, and then potentially use the heat if we're doing urine diversion, and use the heat for thermally inactivating the urine, water condensation and reuse coming off the gases, nutrients through absorption of the biochar, as I talked before, and combustion gases that may be used for household purposes. The urine diversion process considerations are listed here. We first want to look at disinfecting the urine and then recovering the nutrients from the urine, and then plan for the use and proper disposal of the residual liquid material from our system. And we'll compare both the urine diversion and the MIC waste in terms of the efficiency and the cost of the reactors. So this is our kind of first computer-generated view of what we think the system might look like. We'll have a user compartment, a tracker, and a collector. So we do have, in our first version, a tracker, so that we'll keep during that 4 hours movement across the sky to be able to get the most efficient use of the sun. Again, we can have a manual override of the system so that it can be moved manually every hour, or we can display the reactors in an arc so that at one point in time, each one of the collectors is at the most efficient place as the sun moves through the sky. We also have the mechanisms of rotating our carousel, gas and urine diversions, product storage, and then instrumentation and control units. If we're going to use electrical motors to turn the carousel and lower the reactor, then we'll need small solar panels and a battery to be able to do this electronically, but we'll have a manual backup system for all of this. There's several risks associated with the system, and so we've built in preventative measures to deal with many of the risks, but we also have contingency plans in place to be able to deal with problems that might occur, even though our preventative measures haven't worked. So, moving forward, what we do is we want to achieve our technical milestones, our proof of concept, and our prototype. But we know that that's not equal to sanitation problem solved. As a diverse team with extensive experience in the wash sector, we understand that the system has to be affordable, the system has to be scalable, the system has to be robust, and locally operated and managed. So looking forward, we are hopefully at the end, we have the potential for future field testing at the Kampala Sanitation Laboratory in association with Water for People. And then we also want to utilize the university resources at the Mortensen Center for Engineering and Development Communities to look at low-cost, open-source, do-it-yourself alternatives to the system that we're proposing, as well as working with the Leeds School of Business in their social entrepreneur program to look at an in-depth market assessment and feasibility analysis. So with that, I'll take